Is Gary online? Gary Clifford, the next speaker, was A, taken ill, and B, injured, and is now at his home in Atlanta, Georgia. Hi, Gary. Can you hear me?
I can.
So
How are you?
in these respects, Gary stands out like a sore thumb. Do you want to hold up your hand? You will see in a moment that his thumb is heavily bandaged. And yes, there we go. There we go. Okay. Gary is a maven in signal processing relevant to physiological monitoring, and after years at Oxford and MIT is currently in Atlanta, where he is the interim chairman of the joint Georgia Tech Emory Department of Biomedical Informatics. Take it away, Gary.
Thank you, Randall. Again, I apologize for not being there today. Randall asked me to talk a little bit about a lot of things, and I apologize for the all-encompassing title of this. But I think I was trying to get at what Randall was hoping I would talk about, which is how do we share data? I think that's the right title for this, but this is the way that we do it, I think. But before I do that, I wanted to talk a little bit about some of the background on this. So skipping to the first slide, we have been running for several years the PhysioNet challenge. In fact, the PhysioNet challenge has been running for 16, 17 years now. And if you're not aware of PhysioNet, it's a large resource of public data that has annotations, it has signal processing code and machine learning code for classifying data, open source and posted with it, plus publications that describe how to use it, different peer-reviewed publications and also how-to guides. Since 2000, we've been running a series of challenges where we put up basically a gold standard database that's been expertly annotated usually, and we ask the community to address some particular problem that we feel has been unresolved for a significant amount of time. And I'm not sure how well you can see the text up in the top left-hand corner, but it varies from detecting sleep apnea from the ECG to identifying and predicting spontaneous termination of AF to hypertension to mortality prediction in the ICU to classifying abnormal heart sounds, which is this year's challenge. And in particular, last year's challenge was talking about addressing the problem of false alarms in the ICU. And I wanted to talk about that just very briefly to give you some background on where we're going with a data sharing initiative and how I think that this could become a general data sharing initiative. I should say that I take no responsibility for PhysioNet and the setting up of PhysioNet. This was George Moody, Roger Mark, and Eric Goldberger at MIT and Harvard. And incidentally, they won the American Association of Medical Informatics Key Award for contributions to patient safety this year for this particular resource, which has really been a lifelong passion and a lifelong contribution of these guys and the team that they've assembled around them. And I was just lucky enough to work with them and for them for about 7 years, the last decade. Since then, I've become very heavily involved in the PhysioNet competition. So this is something I'm very passionate about. The 2015 PhysioNet challenge involved taking ICU patient data that was multi-lead ECG, photoplethysmogram data, and arterial or other pressure signal data. And looking at sections of data where there were life-threatening arrhythmia alarms, things like asystole, ventricular tachycardia. But typically, monitors only look at the electrocardiogram to do this. They're univariate signal processing approaches. And so a huge fraction of these alarms tend to be incorrect. They're tuned to be extremely sensitive, but as a result, not very specific. And up to 95% of these are actually false alarms in the case of asystole. It's a little bit lower in the case of other alarms, but there's an enormous number of false alarms. So the challenge was, can we automatically detect false arrhythmia alarms by taking advantage of all of the parallel data. So here's a good example on the right-hand side. You see a ventricular tachycardia alarm has been issued. You can see it's got 3 stars in front of it. That means it's life-threatening in the Philips monitor vernacular. And you can see 2 pressure signals at the top of the tracing. The first one is a photoplethysmogram, this pulse oximeter on the finger. The second one is a ventricular tachycardia alarm, a blood pressure waveform. A blood pressure waveform, which is an arterial catheter that's indwelling. And the bottom 2 tracings are the 2 leads of ECG, which have caused the ventricular tachycardia alarm to be issued. And in this case, you can clearly see that there's a nice pulsatile waveform on the blood pressure tracing, the second trace down. So we can be pretty sure that this is a false alarm. The heart is pumping quite regularly, and it must be supplying oxygenated blood because the pulse oximeter looks fine as well. So everything's fine with this patient. It's just an abnormal movement or a typical movement on the electrodes, probably somebody moving around, or they've got some muscle artifact contraction and it's causing a false alarm. This is pretty typical. I'm going to give you another example now and get you to see if you can guess which alarm this is. So this, the title of this slide says the 2015 PhysioNet Cinc Challenge Alarms. And you'll see that we have 5 types of alarms in this challenge: asystole, extreme bradycardia, extreme tachycardia, ventricular tachycardia, and ventricular fibrillation. The next slide, we're looking at a Vtach example, and I want you to guess whether this is true or false. In the middle of the screen, you see the ECG. There's 2 ECGs at the top of the screen, and they seem to descend into ventricular tachycardia or VFib. It's not really sure. The algorithm doesn't differentiate between the 2. And you can see on the bottom tracing there's a little 3-star alarm. It says VFib stroke Vtach. And the algorithm thinks, because of the ECG, that this patient is in ventricular fibrillation. If you don't know what that is, it's basically a conduction abnormality that's causing the heart to pretty much squirm like a bag of worms. And the top 2 tracings look to be very clearly in this sinusoidal oscillation, which we typically see in Vtach. So the question is this a true alarm? And the clue is in the blood pressure tracing. Now, this one's a little harder because actually, if you look down, and we'll go to the next slide here, and you can see I'm pointing down to the relevant piece of blood pressure. And you can see within that blood pressure tracing, there is some abnormality. But it turns out that even though it's abnormal, it still indicates that there's some pump function. So the point I'm trying to make here is that abnormality can often be simultaneous with noise. There is no such thing as independent noise. And in physiology, you always get some kind of relationship. So you have to be a little careful here. What's happening is that there's probably some chest pain on this individual. He's got some ectopy, and he's actually reacting to that by probably pulling the electrodes. So what did we do about this? Well, we decided that we would post some public data and divide this into a public training set and a hidden test set. So we had 750 training records, 750 patients, where we had hand annotated by multiple experts whether it was a true or false alarm, and then 500 hidden test records. Each recording had multiple channels of data, whatever was serendipitously available. It had the type of alarm and whether it was true or false. And then we challenged the entrants to develop an algorithm that weighted the false positives much less than the true positives. So in other words, what we were trying to do was ensure that we pushed the entrance around the receiver operated curve. So if you look at the top right-hand corner of the tracing here, you can see that the receiver operated curve for a particular classification algorithm. And what we were doing was, instead of picking the point closest to 1, 1, 0 on the sensitivity positive predictivity curve, we were actually trying to push the contestants towards the top right-hand corner and ask them to be extremely sensitive, but also very, very specific. That was the challenge here. There were two events, a real-time event where we gave them 10 seconds since the initiation of the alarm, and which is the AAMI FDA guidelines. And we also gave them a retrospective challenge where we gave them some extra information after the event to see if a longer window would actually improve the accuracy of the algorithms. And I'll come back to why we did that in a few minutes. So the timeline for this was that we had 6 months for entrants to enter this. This is very typical, February through August. 30 international teams competed, 215 open source entries and 29 closed source entries entered this. And that's very, very important. We don't prohibit people from entering closed source entries, but it's surprising that we usually have a contest where we award different prizes for open source and closed source entries. We encourage the use of open source entries if we can to try and increase the dissemination and the scientific rigor of it. But we're trying not to prevent people who are trying to commercialize algorithms as well. So we had several winners in each category. We awarded prizes to the top three. Notably, the winners often just swapped positions in the different events. This is for the retrospective and the prospective challenges. And then we have this table of the true positive and true negative rate and the resultant score for each of the entrants. And we can see that on average, people were scoring around about 80%. But I want to draw your, or the maximum was 82% in the real-time event. I won't talk about the retrospective one for a minute, although we had a 99% true positive rate in one of the retrospective events. But in the real-time event, we had this 82% winner. But if you go down to the last two lines, you see something where we have an 84.26% accuracy or score for a voting algorithm, and I've called it n equals 13, because if you skip to the next slide and look at this graph of voting performances, you see that what I've done here is ranked all of the algorithms in terms of their accuracy on the training set, and then voted them together sequentially and reported their consensus score on the test set. So what this does is give us an idea of how well any combination of these algorithms would do in order to provide a group scoring system. And what happens is you always get a subset of the algorithms that if you vote them together will do better than any one of the single algorithms. That's the point of this graph, is that there is a way to pull the algorithms and get higher, more accurate scoring system. So I'm going to come back to that. This is a very important point. But the conclusions of the PhysioNet challenge were we should consider extending the FDA minimum window to 20 or 30 seconds. This is because the retrospective analysis gave us a much higher score, and there is really no reason that we shouldn't have a larger window time on these particular events. Most clinicians agree that you could wait another 20 or 30 seconds. It was just arbitrarily picked decades ago. So that's one of the things that I think we can address with these kind of pooled data approaches, is readdressing these kind of guidelines through competitions. We also saw that the machine learning approaches were often overtrained in these particular data sets. So what we've done now is moved more and more towards using larger and larger data sets, because everybody and his dog nowadays is trying to use a machine learning approach to solve these problems, which is intuitively the right way to go. But of course, the number of patterns that you have to achieve this is one of the key points. And without actually having enough big annotated data, we're never going to get there. Voting algorithms worked the best, but there's a key problem here, which is that you can't just vote all the algorithms together. You need to be clever about the way that you vote them together. And I'm going to come back to that again in a second. We said that we need more data. And I think the approach to this is not to simply wait until we have more data, but to crowdsource this over time. And this is part of the framework that I'm going to be talking about. And in particular, we need to develop better voting algorithms. So I'm now going to talk about how to improve the voting algorithms in the context of this, this group data generation system. So I'm going to start with a simple QT estimation example. So you can see at the top there, there's a hand drawing of 3 ECGs. If you're not familiar with the ECG, have a look at the right-hand corner. That is a stylized ECG, which is this recording of microvolt fluctuations across your chest, which is indicative of how the heart's working. And one of the key things that we need to measure is this QT interval. You can see it annotated slightly. It's very small, but it's that bottom scored segment in the top right-hand corner. It goes from the start of the big spike to the end of the last bump, if we want to be technically correct about describing that. And what I did here was draw 3 exemplary ECGs. And this came as a discussion that I was having with a colleague where I postulated that doing something, annotating something like the QT interval could be done simply by novices. And my colleague objected and said that he didn't think this was possible. So I drew out these 3 ECGs and I showed them to 2 random people that happened to be walking by, who I knew for sure had no experience of annotating the electrocardiogram. And I'll explain why I know that for sure in a minute. And I asked them to look at this particular tracing, and I told them to look and mark the start of the big bump and the end of the last bump. That's essentially how you score QT intervals. Oh, by the way, the importance of the QT interval is if it becomes prolonged, then that means you're likely to have a life-threatening arrhythmia. So measuring this interval accurately is extremely important, and many drugs get thrown off the market for these intervals being prolonged. So if we go to the next slide, you see now the test data in green, and this test data I drew out to be pretty similar to the training data. I tried to match the patterns quite closely, and I asked my 2 annotators to show me where the end of the last bump was, which is the key problem in QT interval measurement. And annotator B, as you can see, did a very accurate job of finding the end of the big bump. And annotator A did a pretty poor job, actually. He always scored the end of the last bump. Annotator B, she was extremely good at this. So actually what I did was take annotator B and say, okay, you've never seen these patterns before, so I'm going to give you 3 new patterns, 4, 5, and 6, and ask you to find the end of the T wave in this one. And again, she did an excellent job of this. And the only difference between these 2 annotators, and this is the reason how I know that they were ECG novices, is that annotator B was aged 5 3/4 and annotator A was aged only 3.5 years. So this was my friend's children that I'd asked to do this. So at this point, I managed to convince him that you could potentially take a bunch of novices and try and derive an accurate crowdsourced measurement. The question, of course, is how do you know who's correct? Is annotator A correct or is annotator B correct? Well, as we often know, the wisdom of crowds can tell us what would be the right answer. And if you took enough annotators, you could probably just simply take the median. But it turns out that it's not quite as simple as taking the median of a bunch of votes, because we have schools of thinking and people don't tend to act independently. And also they can be thrown off by different contexts. So skilled annotators will give you one distribution of annotations, and unskilled annotators will give you another distribution. So often this can cause a large bias in your system. So what we need is actually a framework that takes account of this. So the other thing we have to ask is, of course, how many non-experts does it take to make an expert as well? So we're saying that we're trying to take novices, or if you like, you can think of novices, you can think of algorithms as novices as well. So in other words, anybody who's not a qualified electrophysiologist or ECG reader, we would talk of as being a novice in this context. And an algorithm would certainly be one of those contributors. So the key is, how do we develop an algorithm that allows us to vote together accurately and also identify what the minimum number of annotators is that we need in order to get an accurate read on something. So in other words, how do we pull all our data together, throw a bunch of algorithms at it, and or a bunch of humans, and know for absolute sure, or within a certain accuracy tolerance, that we have got the right answer or the best answer that we could possibly hope for. So there is a nice framework for doing this. We've been developing this over the last 5 years. First of all, you weight each annotator by the inverse of their variance. So what do I mean by that? Well, that's like robustly squares. What you do is you take everybody's annotation and you find the mean of that. And then you measure the distance between each annotator to the mean for each of their annotations. And then you reweight them by 1 over that. So anybody who bounces up and down above and below the mean a lot ends up getting a low weighting, whereas somebody who sits very nicely in the mean gets a very high weighting. Then the second thing is to add in some context. So what we do is we change the weighting as a function of some objective parameter like signal quality. So if we can measure the signal quality, which we developed algorithms to do in an objective manner, we can now say that annotator A functions very well when the data is clean, but when the data is very noisy, he gives us a very inaccurate reading. And vice versa, we can find that annotator B is very good, whether the data is noisy or not. And then appropriately weight the annotators to give us the maximum amount of information. And then thirdly, we weight the function, we weight the annotation as a function of their vigilance, so their minute-to-minute behavior and their ability to learn the actual problem as they go along. Now, number 3, we haven't implemented yet, but that's one of the key issues, is to be able to do this dynamically as somebody waxes and wanes their ability to actually do the annotation. So we're using eye tracking and mouse tracking to do that at this point. So the main point of this, the fourth point, is that this is completely unsupervised. We have no need for objective labels in order to do this because it's an expectation maximization approach. You're iteratively reweighting everybody based upon your distance from the overall mean. And you're doing it as a function of context, both of physiology and signal quality. So that's extremely important. Okay, so how did we apply this? Well, we took the Challenge 2006 database, and there's a reference for the absolute details of this, but what we did was take a QT database of 548 records with over 38,000 QT annotations in there. And they were annotated both by 20 experts and 69 automated algorithms. And of the manual algorithms, the best root mean square error, in other words, the minimum error, the average error that any individual expert managed to achieve was 6.65 milliseconds. So just to give you some context, the QT interval is usually about 300 to 450 milliseconds long. So this is a very small error, yet it can still be significant. And in general, most people will between 20 and 50 milliseconds, which is a significant error. The automated algorithms produced errors anywhere from 20 to 100 milliseconds, but the absolute best algorithm was 16.36 milliseconds. Our voting algorithm was able to achieve 6 milliseconds in the manual when voting the manual annotators together, and less than 14 milliseconds with the automated algorithms. So the point here is that we're always able to achieve a better score than the best of the best in your entire data set, even without knowing who that person is. So we're completely blind to who performed well and who didn't. And the expectation maximization approach guarantees us the ability to beat everybody and increase the amount of total information. So even identifying who is the best expert within the entire data set wouldn't help you beat our algorithm. What's more, if you look on the right, you can see that as we decrease the number of annotators going from right to left, this is a consistent trend, and we're always able to improve the level of the root mean square error, reduce the root mean square error, no matter how many annotators we use. And what you can do is do a bootstrap analysis to find out exactly what your expected error would be for a given number of annotators. So that's absolutely key. If we want to pull our data together and then be absolutely sure that our annotations on these data are accurate within some pre-specified tolerance, we can do exactly that. We can run bootstrap simulations and identify the exact level of confidence that we have about any given set of annotations. Okay, so where does this leave us? Well, what I'm proposing is that we create a large-scale data, code, and annotation sharing platform, very, very similar to PhysioNet, but we use some kind of cloud service where we can share both the data and the cloud services on top of that. So each of us can pull our data into it, and our annotations and our algorithms, either privately or publicly, and then cross-share the resources to be able to compute on that, where you're still paying for your own compute time, essentially. So we've built a preliminary version of this using Amazon Web Services. The American Association of Medical Informatics has funded us to develop this. And the idea is that we're going to upload data code and annotations of ICU data in the context of false alarms. So in other words, building off the 2015 challenge, this is something that they identified as being something critical and important and wanted us to build this out. AWS is going to be our collaboration platform for this. And the way it's envisaged is that every time a new piece of data is uploaded, it can be assessed by hundreds of algorithms that have been contributed, or vice versa. You can upload an algorithm and have that assessed on the entirety of the data that's already sitting there in the cloud. Then, anytime that we feel that or we identify that a new piece of data has a large variance on it amongst all the algorithms, and that we're not getting a stable consistency between a quorum of algorithms on a particular annotation, that's the point where it can be pushed to experts for further review or held in a holding area for anomalous computing. And then finally, one of the facets of this is that users will be able to hide data that is treated as an unseen data set for you. So in other words, I could post all of my ICU data, but not allow you to actually touch it, but you could still upload your code, run it on my data, generate answers, and have those answers pushed back to you as a set of performance statistics. So that's one of the key issues. Is I think we have this this worry, particularly by our institutions, that how do we share data with each other without overstepping the boundaries and giving away the baby with the bathwater? Everybody, I know my institution, for some reason, has it in their mind that the raw data is extremely valuable, and they don't realize that its value is only in what you understand about it, and the value is really in the algorithms rather than the code itself. But the institutions have this kind of intrinsic resistance to sharing the data, and I think this is one way that we can get around that. And this is actually true of the, even more true of the equipment manufacturers. So I've been sitting in conversations with GE and Philips and Datascope, Mindray, and a few others, and talking about how we can build a trust system that allows them to run their code on other people's data and have other people run their algorithms on their data without giving away any proprietary information and giving their competitors a clue about how good or bad their algorithms perform. And I think that's absolutely key to being able to share our data in a trust network. There are a couple of other issues as well. So the other things that we need to build into this, and this is on the roadmap, is that we need to build into the streaming data, electronic medical record data. So we need to combine the two together and be able to upload demographics and history to allow dynamic modification of thresholds on an individual basis. We're also talking about how we can work with the manufacturers so that events such as life-threatening arrhythmias could be automatically uploaded in a de-identified fashion directly from the bedside monitor into this cloud system for automatic review by a whole series of algorithms and potentially humans. In this way, we end up crowdsourcing the annotations, and we build a large collective system with a lot of accurate annotations on it. And we can also solve other issues like aftermarket vigilance. If you've worked with medical companies, you realize that they're often driven to produce modifications of their algorithms by customers who perceive that there's something wrong with their algorithm, yet don't really have any statistical data to back that up. So they end up going and spending a lot of time with a high-paying customer to try and alter the algorithms to assuage their paranoias. But what this does is drive the algorithm for that particular group into a local minimum, where it's actually behaving in a highly tuned way that makes that particular group of people feel better about the algorithm, but doesn't actually improve the algorithm's overall performance. In fact, worsens it. And the fun thing that I'm able to announce today as well is just this week, Amazon agreed to host the whole of PhysioNet for a period of 2 years. So we now have the ability to push the data into the cloud for free and have it hosted by Amazon. And this is something that I can envisage as being able to scale up and use as a generalized service. Now, I'm not saying that necessarily we have to fix on Amazon to do this, but this is the kind of thing that cloud service providers are getting excited about at the moment. They see a potential business model where people will come to the data and compute on the data, and therefore they're willing to host this data for us for free, which I think is an exciting prospect at this point. It solves the storage and the compute problems simultaneously. Yet, curating and running the challenges is still vital. I don't think we can just simply keep dumping data into the cloud and hope that that's going to solve all our issues. So I realize I've been running for about 30 minutes now. And so I'm going to ask Randall whether he wants me to talk a little bit more or whether what the timing is like at this point. Because I realize I've got no visual or audio feedback really from the audience either.
Well, Gary, can you hear me?
I can, yeah.
Okay, so that was outstanding. No, you don't need to say any more. This last bit of news is very much in keeping with the tenor of the discussions today about sharing analytics and sharing data, and there you are. That was outstanding, and thank you very, very much for all the extra effort required to do it in this way.
Thanks very much, Randall. And I'm sorry I could